All right, today in the lab, we're going to be collecting some data that will allow us to determine the spring constant K. It's really a measure of how stretchy or stiff a spring is. You can imagine that springs have different amounts of stretchiness based on the type of metal they're made out of, how tightly they're wound, thickness of the wire, the metal that's made out of. And so we want a way to sort of quantify how stretchy it is. And if you think about the conclusion that we're going to reach, we're going to sort of determine the spring constant. Here's our spring right here that we're going to test today. It's going to be measured in units of newtons per meter. Newtons per meter. So it's really telling us how many newtons of force does it take to stretch the spring out 1 meter, right? So as you apply a force, it stretches, and to keep stretching it, you got to apply a greater and greater force. The force that we apply to the spring is directly proportional to its extension. When that is true, we say that the spring obeys Hooke's law. Okay? Note that we're talking about elastic and plastic deformations. So as we apply force in the form of weight, right, we're going to have mass and therefore weight to the spring. The spring sort of also has a force in it, right? It's trying to sort of pull back in the direction that we apply the force to it. That's why this negative sign is here, because the force in the spring is actually always opposite sort of the extension, right? So as we extend the spring, what's the spring want to do? It wants to kind of pull back. So that's why when we remove the force or remove the weight, the spring returns to its original shape, hopefully. And that we say is a elastic deformation. There is a point that we could overwhelm the structural integrity of the spring, add so much force to it that would just stretch the spring out, right? If you've ever sort of done that before, you know the spring is never quite the same again. It's never going to return to its original shape. And so no longer will the force be proportional to the extension. It's like we've unwound the spring, and now as we apply a force, it's just going to completely unravel. Okay, so when this is true, when the force is proportional to the extension, we say the spring obeys Hooke's law. There's like a region of force that we could apply to a given spring where it will still obey Hooke's law. And like I said, there's also a point we could overwhelm, you know, that integrity of the spring and stretch it out, you know, beyond its point of elasticity. Okay, the elastic limit is that point that if we, you know, exceed it, it will be a plastic deformation that will never return to its original shape. Okay, so you can kind of take a look at this and think about what data we're trying to collect here, the analysis at work. As a suggestion, I think we should measure and record the original length of the spring from endpoint to endpoint. Now you might say, well, why not measure it like the springy part of the spring, right? You look at the spring, it's got like these loops that allow us to, like, you know, hook it onto our lab apparatus, but the spring is really this part here. As we add force to it, as we add force to the spring, it's going to be more and more difficult to judge sort of where is the top and bottom coil there. And then that's another judgment that we're making. Every time a human being makes a judgment, we're introducing uncertainty. So the only judgments we want to have to make is like, where does the end of this spring line up with my ruler? And where does the end down here line up with my ruler? And that's a consistent way to sort of always measure the length of the spring, right? So from end to end, you can see that's how we're measuring the length. If we know the original length, what we really care about is the extension, X for extension. Elongation, if you prefer, like, hey, it should start with. So the elongation or the extension X, we're going to plot X on the X-axis. That's kind of what I like about this lab. We call it plot X on the X-axis. So X for extension. And it's just going to always be the length that we measure as we add weight to it, minus the original length, and that's going to stay the same. So we don't really need that in our data table. That's why I put it up here. Now, why did I put L naught is the way we would read this, like the length with nothing on it, right? So this is the length where there's some weight, some force onto it. So L naught is just going to be some length that's not going to change. So it's not like in my data table, but I want it right above this one. Why? Why did I decide to put L naught like above this column in my data table? Correct. I think an e-learner at home was thinking, because you're going to subtract that from this, to get X, and that goes here. Good job. Ultimately, we're going to plot the force, which is the weight. So from the mass, we'll have to calculate the weight. Last lab, the friction lab, I was friendly enough to like put an equation. Even the ballistic pendulum lab was a bunch of equations. Here, I'm expecting you to know how to do that. Okay, how do we calculate the force due to gravity? Oh, there's a big clue right there. How do we calculate that from the mass? All right. We want to measure the original length. We'll measure the new length. As we add weight to it, calculate the extension, and then we'll plot those extensions as a function of the weight, the force out. All right, so force against extension, because theory suggests force equals kx or negative kx. Again, the negative sign is just indicating the opposition of these vectors. The force opposes the extension. For compression, think about we could either have a tensile force that we're adding, right, we're stretching it out, or we could have a spring that we put a compressive force to, and we sort of squash it. Either way, the extension or the compression, right, the direction of how the spring is changing its length, the force in the spring is always opposing. All right, so like you compress a spring, it wants to push back. You stretch a spring out, it wants to sort of pull back. All right, so that's where the negative sign. We don't need to worry about like, oh, we're going to get a negative slope or anything like that. Okay, we would expect a positive correlation. The more force we add, the longer it gets. This is the independent variable. I know in the past, we've talked about always plotting the independent variable on the x-axis, or we've actually talked about there's no rule that says you have to do that. And so here's yet another lab where I want to plot the independent variable on the y-axis. Why? Because look at this equation. Y equals mx, and x stays as x. Like we could plot, you know, well, I want to plot x here against force this way, and that's fine. You can do that. We'll have the same data available to you. You could decide to plot force here against extension here, but then what's the conclusion going to be? It's going to be 1 over k. You need to report k as your conclusion. K, the spring constant, is some number. How many newtons per meter? How many newtons of force would it take to stretch this spring out all the way to 1 meter? That's what we're going to conclude. Now, I would never want to do that because I'm sure this spring would never go back if I stretched it out that much. But that's why it's like a proportion, right? So we're saying if I were, you know, like to stretch it out 1 meter, how many newtons of force would it take? All right. The mass hanger itself has a mass of 50 grams. And it does extend the spring a little bit. So this is the measurement I want to sort of take first. 50 grams, you can see it a little bit longer, but maybe not noticeably longer, or maybe not enough of a difference to call that the first data point. So I might put 100 grams on for my first data point. All right. I think that works out pretty well there. Got the data table in view. Adjust this thusly and then throughout the lab. Switch that in there. Now these meter rules, it's important to note, it's easy to make a zero error because there's this little sort of metal bracket on the end here. And if we count from 2 centimeters back to 1.5 centimeters, then we realize that the 1 centimeter mark is right there. Now some rulers, here. That's true zero. Just be careful about a zero error there. And to avoid that, you could just say, well, I'll just call 2 centimeters 0 rather than trying to sort of introduce an error in that. All right, and so if I do my best to hold the end of this spring against the 2 centimeter mark, and you use your judgment to say, well, where's the end of the other spring? What would you call that? Spring length. So I say it goes from 2 to 7.4. Trying to be as precise as the instrumentation allows me to be. So if I read this from the 2 centimeter mark to the 7.4 centimeter mark, that's what? 5.4 centimeters according to my trustworthy mental math. 5.4 centimeters. Now we ultimately want the extension in meters. So maybe I want to just call this 0.054 meters here. Measure the lengths in meters. And then I'll just be always taking this number minus that, right? To get this. That makes sense to everybody? What am I doing with the mass? I got 50 grams of mass. This is a 50 gram mass also. So I have 100 grams of mass, but how much weight is that? Okay, how much weight is that? We're starting out with a mass of how many kilograms? If I got 100 grams. 0.1 kilos. Correct, whoever it was. 0.1 kilograms, or 0.100. So if it's 100 grams, right, 1,000 grams in a kilo, move the decimal point back 3 places. That's one way to think about it. Okay, divide by 1,000. So we have 0.1 kilograms. How much weight is that? What gravity field are we in? Remember, this is going to be on YouTube, and they might be watching this in the distant future, where human beings might be in different places, you know, besides just home planet, right? So this is occurring here on Earth. Okay, future YouTube watchers. I got high hopes. For the future. 0.1 times 9.81 meters per second squared here on Earth, right? We're doing the weight mg, so we know the mass, we know gravity is 9.81 meters per second squared here on this planet. 0.981 newtons of force on that spring. Note that it's trying to be in equilibrium, it's bouncing a little bit. Okay, and so if there is a weight of 0.981 newtons acting down, but it's not accelerating in that direction, then what can we say about the force in this spring? Correct, it's equal to it. Okay, it's got to be just pulling back up with the same force, right? If there was a net force of 0.981 newtons, it would accelerate in that direction, right? Things accelerate in the direction there's a net force. And so, yeah, we have that much weight, but the spring exerts an equal force in the opposite direction. And so that's why we're sort of really expressing what's the force in the spring with this equation, right? Even though we're adding weight to it, we know that the force in the spring is equal to it because we trust Newton's second law of motion. But what's the extension? That was the independent variable that I had control over, that I can vary. The dependent variable sort of depends on that. And I guess my apparatus is kind of clumsy for this, or maybe I need a better measuring tool. Clear plastic rule. So the things that you're in control over, I wonder how audio. The things that you're in control over, you want to try to control as best you can. You don't want there to be uncertainty or error in your lab because, like, oh, something I could have easily changed. You know, like if it's clumsy to work with and you have control over it, you know, change it. I kind of prefer the rubber grip here, which is what I put on this end, but I could also, you know, like put it over here. But then it might slide like that, and I was kind of like, so I kind of prefer how that stays a little bit more static there. And I'll just do my best to measure this now. Really what I should do, I guess, is remeasure the original length, okay, because I'm using a new ruler, but these are all calibrated the same, right, pretty standard. And so now I'm getting an entire length from endpoint to endpoint of 10.9 centimeters. So that's the entire length. 10.9 centimeters is 0.109 meters, and 0.109 minus 0.054 a voice says must be
0.055.
Thank you. Don't leave me hanging. Somebody. 0.055 meters. So it went 5 centimeters longer there. You know what it's time for. Time to vary the independent variable. Hooray. All right, this is 100 grams now. 100 grams of mass means I have a total of, still got the data table in there. 0.200 kilograms. Double that number, we multiply that by 9.81, right? We doubled the mass, and so we doubled the weight. So what's the weight now? 1.962. There's a 0 in there to be consistent. What's the new length? $19.5. 0.195. 0.195. Now, what's the extension now? We're still minusing from the original length. Right? In other words, what is the, I could have said, well, let me start with this data point, right? And then it would have went to this length, and it still would be what extension with this weight, right? So it's not like we're subtracting like this from this. It's always this value, L minus L naught, which was constant. And so the extension with 1.962, almost 2 newtons of force in the spring of weight acting down is what extension? 0.195 minus 0.054. 0.141, 14 centimeters of extension. How could we quickly check whether or not we have exceeded the elastic limit?
You would take the weight off.
Are you telling me that a check of an elastic deformation would be to remove the force and see if it returns to its original shape? Is that what your suggestion is?
Yes. Yeah.
I think that's very reasonable. And by your judgment, and even quantifiably so, right? We could ensure that, yep, that's returned to its original shape. We know that with 1.962 newtons of force, we have not exceeded the elastic limit of the spring, but it's still early yet. Time to vary the independent variable. 100. This is embarrassing. These are 100-gram masses. These are 100-gram masses, you guys. And so our first data point, okay, it's not a 50-gram mass. This was 0.15. Okay, this was 0.15. Hey. That's why they make an eraser. Okay, that's an easy. That's going to change, and therefore that's going to change. But this is right. That's all still good. That's good stuff. And then so This was actually 0.150, right? That was 150 grams because it is a 50 gram mass hanger, but that's 100 grams of mass that I added to it. So that's 0.150. 0.150 times G 9.81 is help me out here, class. 0.15 kilograms, 150 grams times 9.81 meters per second squared. This number here should have been 1.4, let's just say 1.47. We're also going to plot this, and then so we say like 1.4715. Are we even going to be able to judge like, oh, it's 0.15, you know, more units on our graph? So that's probably sufficient there. Now, remember what I did? I added 2 of these masses, okay, thinking each one was 50, and each one was 100. So I really added 200 to this, and so the mass there, the correct mass there, was not 200, but rather 200 grams plus 150, or 350 grams, or good old eraser, 0.350 kilograms. And so we'll correct this quickly by 0.35 times 9.81. And everybody with a calculator or really good mental math capability will know that that weight is 3.43 newtons. Still good, right? But we would get a completely incorrect answer. That's an example of like a systematic error, okay? Which I intentionally included in this lab today to try to illustrate the point that a systematic error is one that you're in control over, right? But just by being a little bit more careful, by choosing better apparatus, instrumentation, reading the mass, it's clearly labeled on the mass, 100 grams. Having a little bit of sense that this feels heavier than 50 grams, you should know that, things like that. All right, so clean that up. All right, so now we are 350 grams. That was there, 0.195. Now we're going to vary this. Anybody else hear that too?
Yeah.
It's for next door?
No.
Oh. All right, we got 350 grams. I'm just going to add 100 grams, okay? 100 grams. So this goes from 0.350 to 0.450. 0.450 times 9.81. Anybody got that yet?
4.41.
4.41 is good. That's the weight acting down on the spring. That's the force in the spring pulling back up. The spring's kind of in equilibrium. Notice how it's oscillating a bit there. Like when you stretch it, remember there's some elastic potential energy stored in the spring. This force did work on the spring, right? Force times distance, so it did work. Work is energy. And so the work that this weight did in stretching out the spring is now equal to the energy stored inside of the spring. And you may notice that there is an oscillation that occurs, right? If you disturb that from its equilibrium position. Perhaps there's a relationship between the period of oscillation and the spring constant. That might be something to consider for future lab day. All right. So now we have 450 grams or 4.41 newtons. And I think I can get at least maybe one more data point with my green rule here. Not get a parallax error. Parallax error is when you're sort of looking like this, so you should be looking perpendicular to the instrument. see, I realized. .3.8. So 0.238 meters. All right, is what extension? Say it again. 0.184 meters of extension. 3 data points. All right, let's see what we can do here. What if I vary the independent variable thusly? It's 250. Okay. You see what I've done here? So I had varied this by putting 200 grams on, right? Two of the 100 gram masses. But I've just adjusted it such that the current mass on the mass hanger is 250, the 50 gram mass hanger and 2 100 gram masses for a total of 250. Would it bother anyone terribly if I put that independent variable down here? Like, come on, I like a nice orderly data table. When you go to plot it though, will it matter? No, you go over this far, you get a number here. And furthermore, it gives us a way to kind of really check this trend. If this holds, note how as we've been increasing the mass and therefore the weight, the length has been increasing and therefore the extension, right? As we've increased the force, the extension has gone up right with it. We've got like data points here. What are we doing right now? We're sort of checking in between, like, does that trend kind of hold? Like, what would we expect this number to be here? Can anybody sort of pinch down on it and say, oh, it should be between what and what? Because we are going to check it. I varied the independent variable, right? There's nothing anybody can do to stop me. So what do we expect here? Yeah, right? And we got this for that, and we got this for that, and so this is in between those two, so the answer is between those two. Let's check it. $15.2 is this number, right? 15.2. Oh, we never calculated that. Not that. 0.152, and so that's good. It's in between these two, right? When we take 0.152, the length minus 0.054, we get and we have that 0.098. Good. That's in between these two. Did anybody multiply 0.250 times 9.81? 2.45, right? Good. So it doesn't matter what order you collect the data in. When you go to plot it, it's going to fall into place where it should. But I know that there are some students that's like, I don't like that. Because you kind of want to observe the trend. You know, some students are kind of think numerically and they're like, oh, I see this. Like, why is this lower? Oh, because this. All right. 250, that's 450, 550. So now we've got 0.550 kilos, which on Earth has a weight of 5.40 newtons. And that extended our spring to 27.7 centimeters, or 0.277 meters. 0.277 meters minus 0.054. 0.277 meters minus 0.054. My birthday. 0.223. 1, 2, 3, 4, 5 data points. Well, I ran out of chalkboard, so I know we like 7, but what are we going to do? Write it over here or something? Forget it. Make a new data table? I suppose we could. Let's see.
Did Miss Kitty's email you?
I don't know. Sometimes in the morning, when we come into work, and the first thing you do is check your email. People will want a bunch of stuff like, hey, this is going on today, and it's all this important information. It's like, I want to come in and start this. I'm supposed to come in and check my email. Like, I'll deal with that at lunchtime. You want me to check it real quick? Well, we're recording. Hold on, let's just stand by on that. And then come to find out like you missed picture retakes and now all the photographer again. So my apologies if that happens, but we're right in the midst of it here. We're almost done. Okay, no more data points. We can plot 5. We can get a line with 5. We can get a line with 2. Right? We can connect the dot between 2 points. Let me not delay further. What I want to try to do here is get a plastic deformation. We saw elastic deformation, went back to its original shape. So let's go ahead and see what I've set it up here. But probably what I should do, honestly. And when I get an email, you'll hear a little ding. Noise, and I'm going to put that. See, that could be it right there. That little ding noise. So now it's like I feel the force per unit area. The pressure. Yesterday's essential question. The pressure to plastically deform this with enough time to check my email. All right, did I already add some weights? So we have 1, 2, 3, 4, 550. This was the last data point, right? 1, 2, 3, 4, 550. 650. 750. 850. slide back this way a bit. Why? Because this thing might just become a projectile. The spring would snap. 1, 2, 3, 4, 5, 6, 7, 8, 50. 950. We will exceed 1 kilo now with 1,050, so 1.05 kilos. Do you think that we plastically deformed this? You think so? Oh, I think you're right. If we were to measure this now, from endpoint to endpoint, it is well over 6.5 centimeters, right? And it started out this morning at 5. So the spring may never do the same again. It's the same too, because I only have 1 day left to retirement. All right. What if I put a Newton meter on it? So we did the friction lab and we pulled it. That's another way to measure the force, right? Like I could add weight to it, so I kind of know how much weight is there. What if I just pulled this thing? Right? You think there's a point that I could overwhelm and plastically deform this? Elastic deformation. Right? And so now it's like a new spring, right? It's not the same as it was before, but it could still go back to its original shape, right? This new shape. But what if I did something like this? So now I've completely brought it to where it's beyond where it's obeying Hooke's law, right? It's nowhere near going back to its original shape. I can measure it right, I can't even use my ruler anymore. Okay, now I do need to use a ruler. So this is by far not the same spring. I basically unwound it, right? Still have some springiness, yeah, kind of, I guess, right? Like I can compress part of it and would want to push back a little bit, right? And so that's an example clearly of a plastic deformation. And we'll end it there. Remember, to conclude your lab, you want to plot force against extension, find the slope of the best fit line. That slope will be your spring constant K in newtons per meter. They'll told us what was the spring constant of this spring, when it was still obeying Hooke's law.